Hello, in this video we'll continue talking about cyclohexane and chair conformations. The notes that I have here are the end of our notes from class on Thursday. So we took 2 line angle drawings of 1-chloro-2-methyl cyclohexane. So on the left here. One has chlorine with a wedge, and a wedge bond indicate that bond is pointing up when we draw the chair conformation. And has a dashed methyl. Then the other cyclohexane has 2 wedge bonds. And so these are actually 2 different molecules. If we draw them with a line angle drawing, the first one has chlorine axial and methyl axial, and the second one has chlorine axial and methyl equatorial. So in this video, I've copied those 2 molecules over, but let's focus on this first one, the one at the top here. Oops. Okay, so we've drawn the chair conformation. We labeled where the chlorine is as carbon 1, and we did that in the chair conformation as well, and that's where we put chlorine. So we have chlorine axial, and the methyl group also axial. And remember, the wedge means it's pointing up, dash means it has to be pointing down. Well, if we draw a chair conformation, so drawing that chair structure again, where we labeled carbon 1 is slightly arbitrary. I put it in the top right corner, but what if we started carbon 1 in the bottom right corner? Then we have 2, 3, 4, 5, and 6. So that means that on carbon 1, there is a chlorine, and that chlorine is pointing up. I know it's pointing up because in the Lewis, or the skeletal structure, it has a wedge bond. So on carbon number 1, the bond that's pointing up is an equatorial bond. Then on carbon 2, we have a methyl pointing down. On carbon 2, the bond pointing down is also an equatorial bond. So in this second structure, we have chlorine equatorial. And methyl equatorial. And these 2, we call these conformational isomers. I'll write that down in a second, or conformers. So these 2 conformers can be interconverted by twisting around the carbon to carbon bonds. I'll show you that if you have your model kit and you make a cyclohexane, make axial bonds with a white atom and equatorial with a red, you can bend and twist the carbon to carbon bonds and convert that into another cyclohexane, another chair conformation where the axial atoms are now equatorial and the equatorial atoms are now axial. So we call these, like I said, conformational isomers. I'll move this down. So isomers are molecules in general that have the same molecular formula, same number of atoms. Conformational isomers have the atoms connected in the same bonding pattern, so the same location of all single bonds. But conformational isomers are molecules that have different energies. So these 2 isomers have different energies, but they can be interconverted by rotating single bonds. And that's what a conformational isomer is. So remember, we previously talked about constitutional isomers. Those are isomers that have the same molecules that have the same molecular formula, same number of atoms, but their atoms are bonded in different locations. Conformational isomers, atoms are bonded in the same location, but they have a different arrangement in space, and those arrangements can be interconverted by rotating single bonds. So both of these structures are valid chair conformations. But they have different energies. One of these is more stable than the other. We'll talk a little bit more about drawing these. So these are called, again, these are also going from one to another is, we say we do a chair flip. So from one, do a chair flip and you get the other. But we'll talk more about chair flips before we talk about which conformation is higher or lower energy. Let's draw the conformational isomer for that second molecule that was in our notes from Thursday. So again, another way to draw the conformational isomer is to take the left and right bonds, so carbon 1 to 2, and looking at this molecule, carbon 1 to 2 and carbon 5 and 4, those bonds, and instead of angling them to the right, we angle them to the left. So often if you're looking in a textbook and they're showing you a chair flip, one will have the left and right bonds angled to the right, and the other will have them angled to the left. And what's happening between these two is you might imagine this top right bond, in this case where the chlorine is, that bond being pulled or twisted, because these are interconverted by rotating single bonds. So these bonds are rotated to where now carbon 1 is lower, so this will be carbon 1 now. Carbon 4 is then twisted up, and that will be carbon 4. So when we renumber, we shift over 1. This will be 1, 2, 3, 4, 5, and 6. So on carbon 1, we have a chlorine pointing up. That is now in the equatorial position. Carbon 2, we have a methyl pointing up, and that is now in the axial position. If you're forgetting where to put bonds, you can go back to the Thursday lecture. And right here we have where substituents exist on the chair conformation. Each carbon always has an axial and an equatorial. If the axial is pointing up, then the equatorial is pointing down. If the axial is pointing down, then the equatorial is pointing up. All right, so again, these are conformational isomers. They're interconverted. We can use an equilibrium arrow here to show that these two molecules are in equilibrium with each other, the two conformations, interconverted by bond twisting. So there are two examples. Let's put some more explanation and words to what's going on here. So chair flips. Cyclohexane. Well, just to think about why we're even drawing these chair flips. Cyclohexane rapidly interconverts between its two most stable conformations. And both of these are chair conformations. Remember, we also talked about boat. The chair conformations are more more stable than boat. So that's observed. We observe that cyclohexane rapidly interconverts between the two most stable conformations. And so to draw a chair flip, we'll do a chair conformation without any substituents first, and then we'll do a chair conformation with substituents. So let's say that we continue with the numbering that I did before. So top right is number 1. In reality, you could number any carbon as number 1 as long as you're consistent between the two conformations. So carbon 1, and I'll go clockwise, 2, 3, 4, 5, and 6. So I mentioned, and I'll draw the same thing, where if we're doing a chair flip, starting from this conformation, what I've labeled as carbon 1, which is top right, the bonds can be twisted, so that becomes the bottom right atom. Carbon 4 twists up to become the top left atom. And so that results in that outside angles being angled to the left. We do the same process where we have two sets of parallel lines. But we brought carbon 1 down, so now where I've just drawn that green circle is where carbon 1 is. So if this is where carbon 1 is, then we can just go clockwise again around the ring. 1, 2, 3, 4, 5, 6. Carbon 4, remember, was the bottom left, and that was rotated up, and that becomes carbon 4, top left corner. Now let's do this with two examples. With one example with two substituents. Drawing an original chair conformation. Let's put top right, we'll put a bromine. And we'll just emphasize, usually we don't draw hydrogens, but the hydrogens are there, so that carbon has a hydrogen in the equatorial position. And then let's do a hydrogen here. And a chlorine. So I've got the hydrogens in blue and the chlorine and bromine in that pink color. So if we number around, start at the top right, 1, 2, 3, 4, 5, 6. If we do a chair flip, we draw the chair with different angled bonds. Now, instead of carbon 1 being the top right carbon, it is the adjacent, what looks to be the adjacent carbon. So bottom right, and then we can continue around. On carbon 1, we had, in the original structure, a bromine pointing up. In the chair flip, the bromine remains pointing up. It's still on carbon 1, so that means it must be in the equatorial position. For carbon 1, the bond pointing up above the ring is in an equatorial position. The bond pointing down, which is to hydrogen, is in the axial position. Then at carbon 3, we have a chlorine that was pointing down. So for carbon 3 in the chair flip, that chlorine is still pointing down, but now it is axial. And the hydrogen that's pointing up is now equatorial. So we have some rules for chair flips we'll write out. to conclude the video. So remember, if we look at bromine, it was pointing up in the original structure, and it's still pointing up in the chair flip. So any atoms, these are for substituents, atoms pointing up remain up. And what I mean by up is just above the carbon bonds within the ring. So atoms pointing up remain up, atoms pointing down remain down. And then notice for bromine, it was originally axial, and in the chair flip it's equatorial. Chlorine was originally equatorial, and in the chair flip it is axial. So atoms in axial positions become in equatorial positions. And then vice versa, atoms in equatorial positions will be axial in the chair flip. And all of this is describing the substituents on the cyclohexane ring. So not the carbons within the ring, but any substituent on those carbons. All right, I'll end the video here, and we'll talk about why one flip is higher or lower energy than another when we are in class on Tuesday.